Data cleaning is a critically important step in the machine learning project. In tabular data, there are many different statistical analysis and data visualization techniques that you can use to explore your data in order to identify data cleaning operations you may want to perform. Before jumping to sophisticated methods, there are some basic data cleaning operations that you should probably perform on every single machine learning project. These are often so basic, they may be overlooked by the seasoned machine learning practitioners. Yet they are critical, and if skipped, models may break or report overly optimistic performance results. Data cleaning refers to identifying and correcting errors in a dataset that may negatively impact a predictive model. Data cleaning is used to refer to all kinds of tasks and activities to detect and repair errors in data. Although critically important, data cleaning is not exciting, nor does it involve any fancy techniques, just good judgment on the dataset. There are many types of errors that exist in a dataset, although some of the simplest errors include columns that didn't confirm much information and duplicated rows. Before we dive into identifying and correcting messy data, let's define some messy datasets. We're going to use two datasets as the basis for the following examples: the oil dataset and the Irish flowers dataset. Columns that have a single observation or value are probably useless for modeling. These columns or predictions are referred to as zero variance predictors, as if we measure the variance, averaged from the mean, it would be zero. So in this example, a single value means that each row for that column has the same value. So for example, pretend one column has a value for 1.0 in the entire dataset. Columns that have single values for all rows don't contain any information for modeling. Depending on the choice of data preparation and modeling algorithms, variables with single values can cause errors or unexpected results. You can detect rows that have this property using the unique NumPy function, and it's going to report a number of unique values in each column. In our example, you can see we're loading the oil spill classification dataset that contains 50 variables and summarizes the number of unique values in each column. When you execute the code, it loads the dataset and prints the number of unique values in each column. You can see that column index 22 only has a single value and it should be removed. Now we could use a simpler approach, and that's to use the nUnique pandas function, and it does all the hard work for you. Our code on screen shows the pandas function. When we execute this example, we get the same results: the column index and the number of unique values for each column. Variables or columns that have single values should probably be removed from your dataset. Columns are relatively easy to remove from NumPy arrays or pandas data frames. One approach is to record all the columns that have a single unique value, then delete them from the pandas data frame by calling the drop function. The code listed on screen does just that. Running the example first loads the dataset and reports the number of rows and columns. The number of unique values for each column is calculated, and those columns that have a single unique value are identified. In this example, or in this case, column index 22. Then the identified columns are then removed from the data frame, and the number of rows and columns in that data frame are reported to confirm the change. In this lesson, let's consider columns that have very few values. In the previous lesson, we saw some columns in the example dataset had very few unique values. For example, there were columns that only had 2, 4, and 9 unique values. This might make sense for ordinal or categorical variables. In this case, however, the dataset only contains numerical values. Therefore, only having 2, 4, and 9 unique numerical values in a column might be surprising. We refer to these columns or predictors as near zero variance predictors, as their variance is not zero, but it's very small or close to zero. These columns may or may not contribute to the skill of the model. We can't assume they are useless for modeling. Depending on the choice of the data preparation and modeling algorithms, variables with very few numerical values can also cause errors or unexpected results. For example, I've seen them cause errors when using power transforms for data preparation and when fitting linear models that assume a sensible data probability distribution. To help highlight this problem, or columns of this type, you can calculate the number of unique values for each variable as a percentage of the total number of rows in the dataset. Let's go ahead and do this manually with NumPy. Executing our code reports the column index and the number of unique values for each column, followed by the percentage of unique values for all the rows in the dataset. Here, you can see that some columns have a very low percentage of unique values, such as below 1%. We can update the example and only summarize those variables that have unique values with less than 1% of the total number of rows. When we execute our code, we can see that 11 of the 50 variables have numerical variables that have unique values that are less than 1% of the number of rows. Now, this doesn't mean these rows and columns should be deleted, but they require further attention. For example, perhaps the unique values can be encoded as categorical values. Perhaps compare model skill with each variable removed from the dataset. Let's go ahead and show how to remove them. If we wanted to delete 11 columns with unique values, less than 1% of the rows, the example on screen does just that. Running an example first loads a dataset and reports the number of rows and columns. The number of unique values for each column is calculated, and those columns that have a number of unique values less than 1% of the rows are identified. In this case, 11 columns. The identified columns are then removed from the data frame, and the number of rows and the number of columns in that data frame are reported to confirm the change. All right, let's remove columns that have a low variance in this lesson. Another approach to a problem of removing columns with few unique values is to consider the variance of the column. Recall that variance is a statistic calculated on one variable as the average squared difference of the values in the sample from the mean. The variance can be used as a filter for identifying columns to be removed from your dataset. A column that has a single value has a variance of 0.0, and a column with very few unique values will have a very small variance. The variance threshold class from scikit-learn library supports this type of feature selection. An instance of the class can be created, and we can specify the threshold argument, which defaults to 0.0 to remove columns with a single value. It can be fit and applied to a dataset by calling the fit transform function to create a transform version of the dataset where the columns that have a variance lower than the threshold have been removed automatically. All right, when we execute our code on screen, it first loads the dataset and then applies the transform to remove all the columns with a variance of 0.0. The shape of the dataset is reported before and after the transform, and we can see that a single column where all the values are the same have been removed. We can expand this example to see what happens when we use different thresholds. We can define a sequence of thresholds from 0.0 to 0.5 with a step size of 0.05. We can then report the number of features in the transformed dataset for each given threshold. When we execute the code, it first loads the dataset and confirms the raw dataset has 49 columns. Next, the variance threshold is applied to the raw dataset with values from 0.0 to 0.5 and a number of remaining features after the transformation is applied or reported. We can see that the number of features in the dataset quickly drops from 49 in the unchanged data down to 35 with the threshold of 0.5. It later drops to 31, 18 columns deleted, with the threshold of 0.5. A line plot has been created showing the relationship between the threshold and a number of features in the transformed dataset. You can see that even with a small threshold between 0.15 and 0.4, that's a large number of features, 14, are removed immediately. In this lesson, let's identify rows that contain duplicate data. Rows that have identical data could be considered useless to the modeling process, if not dangerously misleading during model evaluation. Here, a duplicate row is a row where each value in each column for that row is identically the same order and the same column values in another row. From a probabilistic perspective, you can think of duplicate data as adjusting the priors for the class label or the data distribution. This may help an algorithm like a naive Bayes if you wish to purposely bias the priors. Typically, that's not the case, and most machine learning models are going to perform better by identifying and removing rows with duplicate data. From an algorithm evaluation perspective, duplicate rows will result in misleading performance. For example, if you're using train test split or k-fold cross-validation, then it's possible for a duplicate row, or duplicate rows, to appear in both the training and the testing sets. This is going to result in a biased estimate of the performance on unseen data. If you think this is the case or not the case in your dataset or a chosen model, design a controlled experiment to test it. This could be achieved by evaluating model skill with the raw dataset and the dataset with duplicates removed, and then comparing that performance. Another experiment might involve augmenting the dataset with different numbers of randomly selected duplicate examples. The pandas function duplicated will report whether a given row is duplicated or not. All rows are marked with either false to indicate that there is not a duplicate or true to indicate that there is a duplicate. If there are duplicates, the first occurrence of the row is marked false by default. When we execute our code, the example loads the dataset, then calculates the row duplicates. First, the presence of any duplicate rows are reported, and in this case, you can see that there are duplicates. Then all duplicate rows are reported, and in this case, we can see 3 duplicate rows were identified and printed. Rows of duplicate data should probably be deleted from your dataset prior to modeling. There are many ways to achieve this, although pandas provides a drop duplicates function that achieves exactly this. On screen, we have an example of just this function. Running the code first loads the dataset and reports the number of rows and columns. Next, the rows of duplicated data are identified and removed from the data frame. Then the shape of the data frame is reported to confirm the change. When you're modeling, it's important to clean the data sample to ensure that the observations best represent the problem. Sometimes a dataset can contain extreme values that are outside the range of what's expected and unlike other data. These are called outliers, and often machine learning models and the model's skill in general can be improved by understanding and even removing these outlier values. In this lesson and the next few, you're going to discover outliers and how to identify them and then remove them from your machine learning datasets. All right, so what is an outlier? An outlier is an observation that's unlike any observation. They are rare, distinct, or do not fit in some way. Now, outliers can have many causes, such as measurement or input error, data corruption, and true outlier observations. There's no precise way to define and identify outliers in general because of the specifics of each dataset. Instead, you, the machine learning expert, must interpret the raw data observations and decide whether a value is an outlier or not. You can use statistical methods to identify observations that appear to be rare or even unlikely in a given dataset. Now, this doesn't always mean that the values identified are outliers and should be removed. The tools described in this lesson and the next few can be helpful in shedding light on rare events that may require a second look. A good tip is to consider plotting the identified outlier values, perhaps in the context of non-outlier values, to see if there are any systemic relationships or patterns to the outliers. Most of the time there aren't. Before we look at outlier identification methods, let's define a dataset we can use to test our methods. We're going to generate a population of 10,000 random numbers drawn from a Gaussian distribution with a mean of 50 and a standard deviation of 5. Numbers drawn from a Gaussian distribution will have outliers. That is, by virtue of the distribution itself, there will be a few values a long way from the mean, rare values that we can easily identify as outliers. We're going to use the rand_n function to generate random Gaussian values with a mean of 0 and a standard deviation of 1. Then we're going to multiply that by our results, then multiply the results by our own standard deviation, and add the mean to shift the values into the preferred range. The pseudo-random number generator is seeded to ensure that we use the same samples each time we run the code. So the first approach we're going to look at is called the standard deviation method. If we know that the distribution of values in the sample is Gaussian or Gaussian-like, we can use the standard deviation of the sample as a cutoff for identifying outliers. The Gaussian distribution has the property that the standard deviation from the mean can be used reliably to summarize the percentage of values in the sample. For example, within one standard deviation of the mean, it's going to cover 68% of the data. So, if the mean is 50 and the standard deviation is 5, as in our test set, then all the data in the sample between 45 and 55 will account for about 68% of the data in the sample. We can cover more data in the sample if we expand our range as follows. One standard deviation from the mean is 68%. Two standard deviations from the mean is 95%, and three standard deviations from the mean is 99.7%. A value that falls outside three standard deviations is part of the distribution, but it's an unlikely or rare event, and it's approximately a 1 in 370 sample. Three standard deviations from a mean is a common cutoff in practice for identifying outliers in a Gaussian or Gaussian-like distribution. For smaller samples of data, perhaps a value of 2 standard deviations, which is 95%, can be used. And for larger samples, perhaps a value of 4 standard deviations, which is 99.9%, can be used. All right, let's put all this together in an example. Sometimes the data is standardized first, i.e. to a z-score with a 0 mean and a univariance, so that outlier detection can be performed using standard z-score cutoff values. This is a convenience and it's not required in general. All right, we're going to calculate the mean and standard deviation of a given sample, then calculate the cutoff for identifying outliers as more than 3 standard deviations from that mean. We can then identify outliers as those examples that fall outside the defined lower and upper limits. Alternatively, we can filter out those values from the sample that are not within the defined limits. All right, let's put all this together. We're going to use the sample data set we generated earlier. Running our code, we'll first print out the number of identified outliers and then the number of observations that are not outliers, demonstrated on how to identify and filter outliers respectively. So far, we've only talked about univariate data with a Gaussian distribution, i.e. single variables. You can use the same approach if you have multivariate data, i.e. data with multiple variables, each with a Gaussian distribution. All right, let's talk about the interquartile range method. Not all data is normal or normal enough to treat as it's been drawn from a Gaussian distribution. A good statistic for summarizing a non-Gaussian distribution sample of data is the interquartile range, or IQR for short. The IQR is calculated as the difference between the 75th and the 25th percentiles of data and defines the box in a box and whiskers plot. Remember that percentiles can be calculated by sorting the observations and selecting values at specific indices. the 50th percentile is in the middle value, or the average of the two middle values for an even number of examples. If we had 10,000 samples, then the 50th percentile would be the average of the 5,000th and the 5,000 first value. We refer to the percentiles as quartiles, quart meaning 4, because the data is divided into 4 groups, in the 25th, 50th, and the 75th percentiles. The IQR defines the middle 50% of the data, or the body of the data. The IQR can be used to identify outliers by defining limits of sample values that are a factor of k of the IQR below the 25th percentile, or above the 75th percentile. The common value for k is a value of 1.5. A factor k of 3 or more is used to identify values that are extreme values or far out when described in the context of the box and whiskers plot. On a box and whiskers plot, these limits are drawn as fences on the whiskers or the lines that are drawn from the box. Values that fall outside these values are drawn as dots. You can calculate the percentiles of the dataset using the percentile numpy function that takes the dataset and the specification of the desired percentile. The IQR can be calculated as the difference between the 75th and the 25th percentiles. We can then calculate the cutoff of outliers at 1.5 times IQR, and then subtract this cutoff from the 25th percentile and add it to the 75th percentile to give the actual limits of the data. We can then use these limits to identify the outlier values. We can also use these limits to filter out the outliers from the dataset. All right, let's put all this together. Running our code first prints the identified 25th and the 75th percentiles, and then calculates IQR. The number of outliers identified is printed, followed by the number of non-outlier observations. The approach can be used for multivariate data by calculating limits on each variable in the dataset, and in turn, taking outliers as observations that fall outside the rectangle. All right, let's talk about automatic outlier detection. In machine learning, an approach to tackling the problem of outlier detection is one-class classification. A simple approach to identifying outliers is to locate the example that's far from other examples in a multidimensional feature space. This can work well with features with low dimensionality, fewer features, although it can become less reliable as the number of features increases. This is often referred to as the curse of dimensionality. The local outlier factor, or the LOF for short, is a technique that attempts to harness the idea of nearest neighbors for outlier detection. Each example is assigned a scoring of how isolated or how likely it is to be an outlier based on the size of its local neighborhood. Those examples with the largest score are more likely to be outliers. The scikit-learn library provides an implementation of this approach in the local outlier factor class. You can demonstrate the local outlier factor method on a predictive modeling dataset. We're going to use the Boston housing regression problem that has 13 inputs and one numerical target. First, we're going to load our dataset into a NumPy array, separate it into input and output variables, and then split it into training and testing sets. Running our example loads the dataset and first reports the total number of rows and the columns in the dataset, and then the number of examples allocated to the training and testing datasets. It's a regression predictive modeling problem, meaning that we're trying to predict a real numeric value. All input variables are numeric. In this case, we're going to fit a linear classification algorithm and evaluate model performance by training the model on the test dataset and then making the prediction on the test data and evaluate the predictions using the mean absolute error. Just as an aside here, your results are going to vary due to the stochastic nature of machine learning models. When we run our example, we get an MAE of 3.417. Next, we can try removing outliers from the training dataset. The expectation is that the outliers are causing the linear regression model to learn a bit of bias or skewed understanding of the problem, and that removing these outliers from the training set will allow a more effective model to be learned. We can achieve this by defining the local outlier factor model and then using it to make predictions on the training dataset, making each row in the training dataset a normal 1 or an outlier as -1. We're going to use default hyperparameters for the outlier detection model, although it's a good idea to tune the configuration to your specific needs. We can then use these predictions to remove all outliers from the training dataset. We can then fit and evaluate the models as per normal. The update example of evaluating a linear regression model with outliers deleted from the training dataset is listed on screen. Firstly, you can see that the number of examples in the training dataset has been reduced from 339 to 305, meaning 34 rows containing outliers were identified and deleted. You can also see a reduction in MAE from about 3.417 by a model fit on the entire training dataset to about a 3.356 on the model fit on the dataset with outliers removed. Real-world data has missing values. Data can have missing values for any number of reasons, such as observations that are not recorded and data corruption. Handling missing data is important, as many machine learning models don't support data with missing values. In this tutorial, we're going to use the dataset called the diabetes dataset. That's been widely studied in machine learning circles since around 1990. The dataset classifies patient data as either an onset of diabetes within 5 years or not. There are 768 examples with 8 input variables. It's a binary classification problem. A naive model can achieve an accuracy of around 65% on this dataset. A good score is around 77%. We're going to aim in that region. But note that the models in these tutorials are not optimized. They are designed to demonstrate feature selection schemes. All right, let's go ahead and print out the data, and we can see all 9 input variables are numerical. The dataset is known to have missing values. Specifically, there are missing observations for some columns that are marked as 0 value. We can corroborate this by the definition of those columns and the domain knowledge that a 0 value is invalid for measures, i.e. 0 for body mass index or blood pressure is invalid. All right, we're going to mark these missing values. Most data has missing values, and the likelihood of having missing values increases with the size of the data set. In this lesson, and in the next few, we're going to look at how we can identify and mark missing values. We can use plots and summary statistics to help identify missing or corrupt data. All right, let's go ahead and load our data set into a pandas data frame and print some summary statistics. All right, this is useful. We can see that there are columns that have a minimum value of 0. On a few columns, a value of 0 doesn't make any sense and indicates an invalid or missing value. Specifically, the following columns have invalid 0 minimum values: the plasma glucose concentration, the diastolic blood pressure, triceps skin fold thickness, 2-hour serum insulin, and the body mass index. Let's go ahead and confirm this by looking at the raw data. Our example on screen prints the first 20 rows of data. Running the example, we can clearly see 0 values in the columns 2, 3, 4, and 5. We can get a count of the number of missing values on each of these columns. We can do this by marking all the values in the subset of the data frame we are interested in that have 0 values that are true. We can then count the number of true values in each column. Executing our code prints out the following. We can see that columns 1, 2, and 5 have just a few 0 values, where columns 3 and 4 have a lot more, nearly half of the rows. This highlights different missing value strategies that may be needed for different columns, i.e., to ensure that there are still sufficient numbers of records left to train on the predictive model. In Python, specifically pandas, NumPy, and scikit-learn, we mark missing values as nan. Values with a nan value are ignored from operations like sum, count, etc. We can mark values as nan easily with the pandas data frame by using the replace function on a subset of the columns we're interested in. After we've marked the missing values, we can use the isNull function to mark all the nan values in the dataset as true and get a count of the missing values for each column. Running an example prints the number of missing values in each column. We can see that columns 1 to 5 have the same number of missing values as 0 values identified above. This is a sign that we have marked and identified the missing values correctly. This is a useful summary, as we want to confirm that we've not fooled ourselves somehow. All right, in the next bit of code, let's go ahead and print out the 20 rows of data. Running the code, we can clearly see the nan values in columns 2, 3, 4, and 5. There are only 5 missing values in columns 1, so it's not surprising that we didn't see an example in the first 20 rows. It is clear from the data that marking the missing values had the intended effect. Before we look into handling missing values, let's first demonstrate that having missing values in a dataset can cause problems. Having missing values in a dataset can cause errors with some machine learning algorithms. In this section, we're going to try to evaluate the LDA, or linear discriminant analysis algorithm, on the dataset with missing values. This is a model that doesn't work when there are missing values in the dataset. The example on screen marks the missing values in the dataset, as we did in the previous section, and then attempts to evaluate LDA using threefold cross-validation, and then printing the mean accuracy. We get an error. This is what we expect. We are prevented from evaluating an LDA algorithm and other algorithms on this dataset with missing values. So, let's delve into a few methods on how to handle these missing values. The simplest strategy for handling missing data is to remove records that contain the missing values. We can do this by creating a new pandas data frame with the rows that contain the missing values. Pandas provides the drop-in-a function that can be used to drop either the columns or the rows with the missing data. We can use drop-in-a to remove all rows with missing data. as shown on screen. Executing our code, you can see that the number of rows has aggressively been cut from 768 to the original dataset to 392 with all the rows containing nans removed. Now we have a dataset we can use to evaluate the LDA model. When we execute the code, you can see the accuracy of the model is 0.781%. I would caution you here that removing rows with missing values can be too limiting on the predictive modeling problem, and an alternative way is to immute the missing values. All right, in this lesson and the next few, we're going to talk about statistical immutation. Datasets may have missing values, and this can cause problems for many machine learning models. Therefore, it's a good practice to identify and replace these missing values for each column or input data prior to modeling your prediction task. This is called data immutation, or immuting for short. A popular approach for data immutation is to calculate a statistical value for each column, such as the mean, and replace all missing values for that column with a statistic. It's a popular approach because this statistic is easy to calculate using the training dataset, and because it often results in good performance. As we've discussed, a simple and popular approach to data immutation involves using statistical methods to estimate a value for a column for those values that are present, and then replace all the values in that column with that calculated statistic. It's simple because statistics are fast to calculate, and it's popular because it's become very effective. The most common is called mean value immutation, because you're calculating the mean value. But you can also use the median, mode, or a constant value. All right, so now that we know what statistical immutation is, let's take a look at a data set with missing values. All right, let's do some immutation. In this example, we're going to use the horse colic data set. The horse colic data set describes medical characteristics of horses with colic and whether they lived or they died. There are 300 rows with 26 input variables and one with an output variable. This is a binary classification prediction task that involves predicting 1 if the horse lived and 2 if he passed away. There are many fields we could use to predict in this data set. In this case, we're going to predict whether the problem was surgical or not, which is going to be, I think, column index 23, making it a binary classification problem. The dataset has numerous missing values for many of the columns, where each missing value is marked with a question mark. When we print out the dataset, we can see the rows in the dataset with marked missing values. Marking missing values with NaN, remember NaN stands for not a number, is a loaded dataset using Python is the best practice. Therefore, we can load a dataset using the readCSV function from Pandas and specify NA values to load instead of question marks. Once loaded, we can review the data to confirm that the question mark values are marked as NaN values now. We can then enumerate each column and report the number of rows with missing values for the column. Tying this all together, you can see the complete example loading and summarizing the dataset listed on screen. We can see that the missing values were marked with a question mark character, and they've been replaced with NaN values. Let's go ahead and take a look at the number of columns in the dataset and the number and percentage of missing values. We can see that some columns, i.e. columns 1 and 2, have no missing values, and other columns with indexes on 15 and 21, have many or even the majority of missing values. Now that we're familiar with the horse colic dataset and its missing values, let's take a look at how we can statistically immute them. The scikit-learn machine learning library provides a simple immuter class that supports statistical immutation. Let's explore how to use the simple immuter function. The simple immuter is a data transform that is first configured based on the type of statistic to calculate for each column. For example, the mean. Then the immuter is fit on the dataset, and it's used to calculate the stat for each of the columns. The fit immuter is then applied to the dataset to create a copy of the dataset with all the missing values for each column replaced with the statistic mean, or the statistic values specified. We can demonstrate its usage on the horse colic dataset and confirm it works by summarizing the total number of missing values in the dataset before and after the transform. The complete code is listed on screen. When we execute the code, it first loads the dataset and reports the total number of missing values in the dataset as 1605. The transform is configured, fit, and then performed, and the resulting new dataset has no missing values, confirming it was performed as we expected. Each of the missing values was replaced with the mean value for the column. It's a good practice to evaluate a machine learning model in a dataset using k-fold cross-validation to correctly apply statistical missing data immutation and avoid data leakage. It's required that the statistics calculated for each column are calculated on the training dataset only, then applied to train and test sets for each fold in the dataset. This can be achieved by creating a modeling pipeline where the first step is statistical immutation, then the second step is the model. This can be achieved using the pipeline class. For example, the pipeline on screen uses a simple immuter with a mean strategy followed by a random forest model. We can evaluate the mean immuted dataset and random forest modeling pipeline for the horse-colic dataset with a repeated tenfold cross-validation. That's seen on screen. When we execute the code, it correctly applies data mutation to each fold of the cross-validation procedure. Just to note, as usual, your results are going to vary due to the stochastic nature of machine learning models. You can see the pipeline is evaluating using 3 repeats of tenfold cross-validation and reports the mean classification accuracy on the dataset at about 86.6%, which is a really good score. All right, let's compare different immuted statistics. How do we know that using the mean statistical strategy is good or the best for this dataset? The answer is that we don't, and that we have chosen this arbitrarily. However, we can design an experiment to test each statistical strategy and discover what works best for the dataset, comparing the mean, the median mode, and constant strategies. The mean accuracy of each approach can then be compared. Running our example code evaluates each statistical immutation strategy on the horse-colic dataset using repeated cross-validation. The mean accuracy for each strategy is reported along the way. In this case, the results suggest that with a constant value, i.e. 0, results in the best performance of about 87.8%, which is an outstanding result. At the end of the run, a box and whiskers plot is created for each set of results, allowing the distribution of results to be compared. You can see that the distribution of accuracy scores for the constant strategy may be better than all the other strategies. We may wish to create a final modeling pipeline with a constant immutation strategy and random forest algorithm, and then make the prediction on the new data. This can be achieved by defining a pipeline and fitting in all the available data, then calling the predict function, passing the new data as an argument. Importantly, the row of new data must mark any missing values using NaN values. Running our example on screen fits the modeling pipeline on all the available data. A new row of data is defined with the missing values marked with NaNs, and a classification prediction is made. All right, we've established that data sets that have missing values can cause problems for many machine learning algorithms. Therefore, it's good practice to identify and replace the missing values for each column in the dataset. This is called data immutation, or immuting for short. Another popular approach to missing data immutation is to use the model to predict the missing values. This requires a model to be created for each input variable that has missing values. Although any one among a range of different models can be used to predict the missing values, the k-nearest neighbors, called KNN, has proven to be generally effective, often referred to as the nearest neighbors immutation. Configuration of a KNN immutation often involves selecting the distance measure, i.e. the Euclidean distance, and the number of contributing neighbors for each prediction, the k-hyperparameter for the KNN algorithm. All right, now that we're familiar with the nearest neighbors method for missing value mutation, let's take a look at a dataset with missing values. We're going to use the horse-colic dataset in this lesson, and we've seen this before. The horse-colic dataset describes the medical characteristics of horses with colic and whether they live or died. We're going to load our dataset using the readCSV function in pandas, and then we're going to specify NA values to load the values that are question marks as missing, and then replace them with NaNs. Once it's loaded, we can review the loaded data and confirm that the question marks are marked as NaNs. We can then enumerate each column and then report the number of rows with missing values in that column. Running our code first loads the dataset and summarizes the first 5 rows. We can see that missing values were marked with a question mark character and they've been replaced with NaN values. Next, as we've done before, we're going to list out all the columns in the dataset and the number and percentage of missing values. All right, now that our horse-colic dataset is ready, let's go ahead and use the scikit-learn machine learning library and pull in the KNN immuter class that supports nearest neighbor immutation. The KNN immuter is a data transform that is configured based on the method used to estimate the missing values. The default distance measures a Euclidean distance measure that is NaN-aware, i.e. will not include NaN values when calculating the distance between members of the training dataset. This is set via the metric argument. The number of neighbors is set to 5 by default and can be configured by the nNeighbors argument. Finally, the distance measure can be weighted proportionally to the distance between instances, rows, although this is set uniformly by weighting default, controlled via the awaits argument. Then the immuter is fed on the dataset. Then the fit immuter is applied to a dataset to create a copy of the dataset with all missing values for each column replaced with an estimate value. When we tie all this together and then execute the code, it first loads the dataset and reports the number of missing values in the dataset at 1605. The transform is configured, fit, and performed, and the resulting new dataset has no missing values, confirming it was performed as expected. Each missing value was replaced with a value estimated by the model. It's a good practice to evaluate your machine learning models on a dataset using k-fold cross-validation. To correctly apply the nearest neighbor's missing data and mutation, and to avoid data leakage, it's required that the models be calculated for each column and calculated on the training dataset only, then applied to the training and test sets for each fold in the dataset. This can be achieved by creating a modeling pipeline, where the first step is the nearest neighbor and mutation, then the second step is the model. We're going to use the pipeline class to implement this. For example, the pipeline on screen uses the KNN immuter with a default strategy, followed by a random forest. We can then evaluate the immuted dataset with random forest modeling pipeline for the horse colic dataset with a repeated 10-fold cross-validation. Executing the code correctly applies the data mutation to each fold of the cross-validation procedure. The pipeline is evaluated using the repeats of the 10-fold cross-validation and reports the mean classification accuracy on the dataset of about 86.2%, which is a good score. Now, your next question may be, how do we know that using the default number of 5 neighbors is good or best for this dataset? Well, the answer is we don't know. The key hyperparameter for the KNN algorithm is k. That controls the number of nearest neighbors that you're going to use to contribute to a prediction. It's a good practice to test a suite of different values for k. In our example on screen, we're going to do just that, and we're going to assign k to 1 through 21. Executing the code evaluates each k value on the horse colic dataset using repeated cross-validation. The mean classification accuracy is reported for the pipeline with each k value used for mutation. In this case, you can see the larger k values result in a better performing model, with that k equals 5 resulting in the best performance of about 86.9%. At the end of the run, a box and whiskers plot is created for each of the results, allowing the distribution of results to be compared. The plot suggests that there is not much of a difference in the k value when immuting the missing values, with minor fluctuations around the mean performance. It's common to identify missing values in the dataset and replace them with numeric values. This is called data immuting. Another approach to immuting missing values is to use an iterative immutation model. Iterative immutation refers to the process where each feature is modeled as a function of the other features, i.e., a regression problem where missing values are predicted. Each feature is immuted sequentially, one after the other, allowing prior immuted values to be used as part of the model in predicting subsequent features. It's iterative because the process is repeated multiple times, allowing ever-improved estimates of the missing values to be calculated as missing values across all features are estimated. This approach may be generally referred to as fully conditional specifications, or multivariate immutation by chained equations, shortened to MICE. Different regression algorithms can be used to estimate the missing values for each feature, although linear methods are often used for simplicity. The number of iterations of the procedure is often kept small, such as 10. Lastly, the order that the features are processed sequentially can be considered, such as from the feature within the last missing values to a feature within the most missing values. Alright, so now we have an understanding of the iterative method for missing value mutation. Let's go ahead and apply it to the horse colic dataset. The scikit-learn library provides an iterative immuter class that supports iterative mutation. It's a data transform that is first configured based on the method used to estimate the missing values. By default, a Bayesian ridge model is employed that uses a function of all the input features. Features are filled in ascending order, from those with the fewest missing values to those with the most. Then the immuter is fit on the dataset. The fit immuter is then applied to the dataset to create a copy of the dataset with all the missing values for each column replaced with an estimated value. At the time this course was created, the iterative immuter class cannot be used directly because it's experimental. If you try it directly, you're going to get an error. Instead, you're going to need to use an additional import statement to add support for the iterative immuter class as follows. Tying all this together and executing the code, first loads the dataset and reports the total number of missing values in the dataset as 1605. The transform is configured, fit, and performed, and the resulting new dataset has no missing values, with our output confirming that it was performed as we expected. Each missing value was replaced with a value estimated by the model. It's a good practice to evaluate machine learning models on a dataset using k-fold cross-validation. To correctly apply iterative missing data and mutation and avoid data leakage, it's required that the models for each column are calculated on the training dataset only, and then applied to the train and test sets for each of the folds in the dataset. This can be achieved by creating a modeling pipeline, where the first step is iterative mutation, and the second step is the model. Again, we're going to achieve this by the pipeline class. In our example on screen, we have an iterative immuter with the default strategy, followed by a random forest model. as in the previous lessons. When we run the code, it applies data immutation to each fold in the cross-validation procedure. The pipeline is evaluated using the repeated tenfold cross-validation and reports the mean classification accuracy on the dataset as 87%-ish, which is really a good score here. By default, the iterative immuter will repeat the number of iterations 10 times. Now, it is possible that a large number of iterations may begin to bias or skew the estimate, and that a few iterations may be preferred. The number of iterations of the procedure can be specified via the max iter argument. It may be a good idea to evaluate different numbers of iterations. And we're going to do that in our example below, using the max iter argument from 1 to 20. Executing our code evaluates each number of iterations on the horse-collar dataset using repeated cross-validation. The results suggest that a very few iterations, such as 4, might be as effective or even more effective than 9 to 12 iterations on this dataset. At the end of the run, a box and whisker plot is created for each set of results, allowing the distribution of results to be compared. You may wish to create a final modeling pipeline with the iterative immutation and random forest algorithm, then make predictions on new data. This can be achieved by defining the pipeline and fitting in all the available data, and then calling the predict function and passing new data in as an argument. Importantly, the row of new data must be marked with any missing values using the NaN value. Running an example fits the modeling pipeline on all available data. A new row in the data is defined with missing values marked with NaNs, and a classification prediction is made.